In these next few slides, we'll do a quick summary of what we saw with initial conditions and homogeneous systems here. We had the two eigenvectors in our solution. And from those two eigenvectors, if we have an initial condition that is a multiple of one of the eigenvectors, then the solution is simply c1 e to the lambda t times whatever our eigenvector was. And that implies that it traces out a path along a straight line when we talk about the plane x1, x2. There's no combination, there's no some of this direction and some of that direction. There's only one direction dictated by v, and so we get a straight line coming out and we get a simple particular solution. We can get either one of them by choosing the initial conditions appropriately. What we get with that is these vectors define lines because we can have any multiple of them. So if we take the 1, 2 line here, that's a line defined by the vector 1, 2. And then we take the other line, which is defined by negative 1, 1. That would be the 45-degree line. And then we look at the eigenvalues that go with that. The negative exponentials will approach 0 as t increases. And the positive exponentials here will approach infinity as t increases. And so what that means is if we start on the red line, which is the negative 5 eigenvalue line, solutions will head towards the center. They'll head towards the origin. If you had a solution that started on the green line, the solutions would head outwards. And there's so much fun linear algebra under this, I can't even begin to describe it, but we'll do my best here. Let's take now a case which is off those lines. So let's take the example of 2, 7 we saw earlier, which would be up here. That is made up of some of the green line and some of the red line. Just add the red here explicitly. What's going to happen, once we find out what the coefficients are, there's going to be some green, that's this, and some of the red, less of it. This direction is going to become less important because this exponential is negative and shrinks. So if we think of what's happening to that combination of e to the minus 5t negative 1, 1, this whole thing is heading towards 0, 0. And we're going to add it to something else, which is going to be some multiple of 1, 2. And think of limits and things like that. We're adding a very, very small value in this direction to something that's going to be out in the 1, 2 direction. Well, what would that look like? We would get a curve like so, where we're shrinking in the negative 1, 1, the red eigenvalue direction, and expanding outwards in the green direction. Let's do that for a couple of other points. If we picked a point like here, that solution is going to fade inwards, paralleling the red, because that component is going to get smaller and smaller, but the green component is going to get larger and larger. And if we did it over here, the same thing would apply. We would move outwards in the green direction and inwards in the red line, and we get solutions that look like this. And the details come down to whether it's negative 3 or negative 5t, but this general structure is going to be there for this kind of solution with a mix of signs of eigenvalues. So you can get really interesting diagrams coming out of this, and this is also a springboard for even more complicated nonlinear systems. We do this kind of analysis for those as well. So it's a very, very deep topic with lots of connections going forward, but it comes down to some very, very simple graphical ideas of vectors and components.